All right, section 10.4 is called Measures of Central Tendency and Variation. So central tendency is this idea of how the data sort of bunches up. What is it doing towards the middle of what's going on somehow? And variation is how it disperses from that, how far spread apart something is. Okay, so that's what we're going to be looking at, is how the data bunches up and how the data spreads apart. So we're going to start with the central variation part. There are three measures of central tendency that we're going to look at. The first one is called the mean. This is the one that you reference when you use the word average. When you talk about your class average or something like that, you're talking somehow about a mean score. So it's also referred to as the arithmetic mean. It is the average of the values. We find it by adding the values together and dividing by the total number of values. So if you wanted to know what is your test average in a class, you'd add all your tests together and you divide by the number of tests, right? That's a mean. All right, the second type of central tendency is a median. A median is the middle value. So you have to be careful when you're doing median that the first thing you do is you take the information and you put it in order. Smallest to largest. You could do largest to smallest if you were so inclined. But the idea is that it's the number in the very middle. Okay, so if there are an odd number of numbers, there really is a very middle something. Right? If there are an even number of numbers, even number of values, there is not one number in the middle. There would be two numbers in the middle. So you take those two numbers and you find their average, their mean between them when you're dealing with median. Okay, so you're looking for what is it occurring in the very middle. The median gives us a lot of good information. Like if I were looking at the median test score on a first exam and I wanted to know what that means that whatever score I'm finding, 50% of the people got above that score and 50% of the people got below that score. It's pretty helpful information, actually. It gives me some kind of an idea that mean loses when I average them together. All right, the last one that we're going to look at is mode. Mode is simply the number that occurs most frequently. And this does say number or numbers because you could have something that has more than one mode. It's called bimodal. It had two modes, for example. You could have something where there isn't a mode at all as well. Everything simply does not repeat itself at all. All the scores are different, or all the numbers are different. Mode is also very helpful information. If I wanted to know what the mode was in terms of the class. Okay, so if I wanted to know about mode of a test, in particular if I sort of grouped values together, mode would be telling me something like how many A's I had. That'd be really important information. If I had 20 people in the class and I had 15 people score A's, that'd be great. But the fact that somebody scored a 52 would not be great, right? I mean, like, so somehow when you average things together, you lose some of the information that you gain by keeping it more separated that mode or median would actually tell us. All right, so we're going to actually practice one, okay? So I want you to take these numbers. I want you to find the mean, the median, and the mode. After you find them, I want you to turn to a neighbor and show them what you have and compare. See if you've got the same thing as someone else, okay?
The other question I have is, for the median here, if you have numbers repeating in there.
That doesn't affect the median. The numbers repeating, it's just put them in order.
So if there's two 18s, you leave one of them out? Or?
No, you don't leave them out. You don't leave any numbers out. So if there are repeated numbers, you just include them multiple times when you write them in order.
And you still find just count out middle numbers?
Yes, exactly. You got it. Emily asked me how many decimals. So we're going to go with 1 decimal unless a problem indicates otherwise to us. Okay? So on this one, there's no indication, so 1 decimal will be sufficient for us. So find the median, find the mean, find the mode. And compare with someone. ask me one of my favorite questions. You know, my favorite, well, it's not a favorite question, but it's a typical question. Is what do I show? And what kind of work are you expecting to see? Because with a data set this small, a lot of this you could actually probably do in your head, right? Most of our data sets aren't going to be this small, but what would you expect to see? So for the mean, which let me show you some notation that I haven't shown you before. For the mean, we're going to see an X with a bar on the top of it used for mean. That's what your book's going to use, so if you see that notation. I'd like to know what it was you got when you added all the numbers together. So what did you get? 139. What did you divide by? 7. This is what I would expect to see. Okay? That way, if you made an error, I can know, oh, they counted wrong and they divided by 8. That's the problem. Or, oh, they added it together and they got 142. Somehow they added an extra 3 in somewhere. And so I can actually make some comments back on what that actually is to fix. All right, so what did you get for the average value for the mean on this one? 19.9. I even hear consensus. Very good. All right, for median, your book doesn't use any particular notation for median. And I hesitate to use M for anything because we have mean, median, and mode, which are all M's. And we used M just a little bit ago for slope, right? So we're just going to write out median. What would I expect to see? What do you think you might be expected to show? A list of the numbers in order, yeah. So a list of the numbers in order. And as Andrew talked about, we're going to list all of them, which means repeating numbers that repeat. So I have 12, 17. What's next?
18, 22, 22.
What is the middle number? 18, and it's actually the second 18, right?
Yes.
Okay, we're going to encounter some of this information later. So I'm going to box this in, and you'll see me box something in with this later too. All right, how about mode? Oh, there's 2 of them, aren't there? Why are there 2 modes, Kayla?
Because 18 appears twice and 22 appears twice.
All right, so mode is supposed to be the number that it appears most frequently, and there are 2 numbers that appear most frequently, and they appear most frequently in the same value. Oh, was it 22? Sorry, I stopped listening and started talking, didn't I? Oops. Okay, so 18 and 22. There's no averaging of this going on or anything like that. If I had one number appear twice and another number appear 3 times, we wouldn't list them both. I mean, these are both listed because they both appeared the same number of times, and that same number of times is both the most. Everybody good with that? Okay. Any questions on mean, median, and mode? All right, one other comment. If we had had information given to us that had context here, we would want to be aware of that context. For example, let's say that this is numbers of students that showed up at the teacher education back-to-school meeting. I don't know, something like that. That we would want to write that we would have 19.9 people, but then we'd actually probably want to write 20, right? Because we don't want to say 19.9 people. A little awkward. Agreed? Yeah. What does that look like? We would want to write down 18 people or 18 students. We would want to write down 1822, that kind of thing. So we would want to use the units when there are units appropriate to it. Okay. All right. That is about it for measures of central tendency. So we're going to move into the other part of this lesson, which is, I'm sorry, there's 2 more questions, aren't there, on central tendency. They're not direct correlation to what we did, but they're an extension of it. I remember now. Okay, let's take a look. All right. This one tells you that the mean score on a set of 20 tests, these have context, 20 tests, is 75. And it wants to know what is the sum of the 20 test scores. So we didn't exactly write down a formula, but there is sort of a formula that we could write down for how to find mean. So what do I do to find the mean of a set of data?
You take the mean score times the number of...
You're already answering the next question, which that's wonderful, Amy, but hold tight to that. We're going to come back to that in a second. Just for now, because I don't think everybody's where you are just yet. What would we do to find the mean?
Take the sum of the number of numbers.
Let's call them scores, just because this particular problem has scores in it. So we take the sum of the scores, or values, whatever they are, and then what do we do?
You divide it by the number of scores. Number of test scores.
Yeah, number of scores is good. That'll work. So you take the sum of the scores and you divide it by the number of scores that you're actually calculating from, right? All right, so if we think of it from this perspective, we should be able to put the values they're giving us in here, even though they're not all on the, say, right-hand side of this equation, right? So what is going to go where? Let's start with the 20. Where's the 20 going to go? On the bottom on the right, the denominator. Where's the 75 going to go? On the mean, which is on the, or in the mean spot, which is on the left. So what's missing up here is the sum, and I'll just abbreviate it right now as just sum. So what would I have to do to find out what the sum of these 20 test scores are then? You'd multiply, right? So the sum would be 75 times 20. Now, well, let's get the answer and then we'll talk about what that means. Okay, what does this give me? 1,500. 1,500 what? It's the score, so it's probably in some kind of a points, right? 1,500 points. Okay, do you have to go through this from start to finish? Well, no. Some of you, like Amy was saying, are already jumping down to the end of the result before you got there. Some of you weren't sure how to start to though either, so I wanted you to see where it's coming from, okay? The next one's going to involve a similar idea. This is my attempt to be relevant to Andrew in the class, because it's talking about football, about which I know very, very little. What's that?
Sounds anything about cars in here.
Nothing about cars. Okay, well, I'll try for cars maybe on the next lesson. If the mean weight of 7 linesmen on the team, those are the big guys, right? Is that right? Linesmen? Linemen. Oh, well, no wonder it didn't like linesmen. That's a typo. Wonderful. We'll fix that for next time. Linemen. Evidently, my finger wanted to put an extra S in there somewhere. The lineman on a team is 230 pounds. And the mean weight of the 4 backfield members, is that right?
No, you normally have the book.
There's like different names for each person.
Okay, that's actually straight out of the book. So unless I typoed it, it's at least not my fault.
It's fine.
It's fine. We'll call them backfield members. It's 190 pounds. What is the mean weight of the 11-person team? Okay, so here's what we can't do. We can't just add the 2 numbers together and divide by 2. So somebody tell me why we can't do that. Because there's 11 players at one average weight, and there's only 4 at the other one, right? Or 7 players at one average weight and only 4 at the other. There's 11 players total. Is that right? Yeah, so that's a problem. So what am I going to have to do instead? I need the sum of all what?
You need the sum of the linesmen, all of the weights.
All the weights. Weights. Amy's got weights right there. Yeah, okay. So let's actually write down sort of generally what we want when we find a mean. We did this on the page before. What we really want is we want the sum, in this case, of the weights, right? And we're dividing by the number of players. And Hannah told me just a minute ago that was 11. So the denominator is, in fact, 11. I like that. How am I going to get the sum of the weights? Okay, so if there are 7 linemen, they would have an average weight of 230 each. I could multiply those to find out the sum of their weights. This is basically the last question we did, right? The sum of the scores. And we can add that to what? The 190 pounders, and there are 4 of them. So just so that we can do it in 2 steps, make sure we don't make an error. What do we get on the numerator for this?
2,370.
Okay, is that?
Yes.
Yes, I got a couple people, good. And then we're going to divide that by 11 with 1 decimal if we need it. 215.5 pounds. Thank you, Haley. Pounds. So that would be the average weight of our 11 players. All right. Any questions? This problem has another name, the way we found mean. It's sometimes called a weighted mean because there's a number of people in this case at each of those different weights. It's not called weighted because it's weights. I should have said that. That was totally just the way it worked out. It's called weighted because each of the scores, in this case the 230 and the 190, have different weights, different numbers of people at that value. So, all right, let's move on to variation. Now we're actually ready for that. We're going to talk about lots of different kinds of variation. The first one, the simplest one, is range. You have heard range before in mathematics. Where? What have you heard it in reference to?
A set of numbers.
Okay, a set of numbers. Can you be more specific? It's okay if you can't.
Where I'm subtracted from the smallest number subtracted from the largest number.
That's how we're going to do it here for statistics. There's another place you've probably heard range mentioned, though, too. Probably.
Talk about graphs.
Graphs, like domain and range, right? So range is a concept we use in more than one place, and they're related ideas. We are talking about the one Kayla mentioned here, which is taking the largest value minus the smallest value. And sometimes you're also looking at the span of values. I can't remember. It's when we do an estimation and number theory, which is the Elementary Math 1 course that some of you guys have already taken. We talk about range in that one too, and we don't do it quite like this either. So this one is actually just taking the largest value minus the smallest value. That's considered our range. Very simple calculation. Doesn't really give us a lot of information. Tells us how spread apart things are from the biggest to the smallest, but that doesn't give us a lot of information. These next three and the ones that are on the next slide are all related, and we're going to use them to create a specific type of graph in a moment. The first thing is called the lower quartile, Q1. Q1 is the value below which 1/4 of the values lie. All right, so in other words, if I stood you up here in front from shortest to tallest, and we sort of marked where 1/4 of you are, that would be our Q1 value. We're going to find Q1 in a specific data set in a moment. Q2 is also known as the median. It's the 50% mark, below which 1/2 or 50% of our data lie. And also, if 50% lie below, then 50% lie above. Okay? Q3 is the third quartile. It's the value below which 75% or 3/4 of the data lie. Okay, so this marks it off into sort of quarters of information. The interquartile range then, like range before, is the difference in two values. It's the difference in the first quartile Q1 and the third quartile Q3. So if we subtract Q3 minus Q1, we find the IQR, or the interquartile range. Two other pieces of information that we're going to use are called the lower extreme and the upper extreme. All these are is the largest and smallest data value in your set. Lower extreme is the smallest value, upper extreme is the largest value. All right, so I think that's 6 pieces of data, 6 pieces of information, excluding range, that we talked about that are specifically related to the last data or last piece of information on this slide, box plot. A box plot is a graph that's created using those 6 pieces of information, and one could say it uses the range to some degree as well. In particular, what it really uses is it really uses the lower quartile, the median, the upper quartile, and then the lower and upper extremes. IQR is there, the range is there. You don't usually see them marked, but they're there. But those are the data values that you need in order to create what's called a box plot. And I think that's what we're going to do next. We're going to create that box plot. Sure enough. It does, you bet. Right. Yeah, so back here, this is abbreviated often as IQR, interquartile range. All right, this data set should look familiar. Does it? Yeah, we already used it once before. No reason to change the data set. We can do some more stuff with it. We put it in order before, and that was helpful for finding the median. We're going to put it in order again for the exact same reason. It's going to be helpful in finding the information we need. What's next? 22? And then my 30? There are, you're right. Okay, so one of the things that we did when we looked at this is we found the median to be 18, right? So it means that half of the data values are below that value and half are above. And we sort of exclude the median itself because it's sort of in between, right? Okay, so excluding the median now, so cover it up in what you're thinking. You have 3 values below, correct? What is the middle value? 17. This is Q1. Okay, above, the 3 values above. The middle value is 22, the second 22. Yeah, so this is Q3. So far, so good? Now let's just talk about what would happen if we had started out with an even number of values. So I'm going to erase this in a moment, but I do want you to jot this to the side. We'll use the same values that we already have, and we're just going to add one additional value somewhere. We will add it before the 12. Yeah, just for fun. Let's put the number as 10 before the 12. I just want an even number of values, okay? So that'll work. Where would my median fall then? It would actually be between the 18s. So right here would be my median. And if the two numbers were actually different, we would average them. If you average two numbers that are the same, what do you get? Same thing. So the median would still be 18. So that actually didn't change. But here's something that did happen differently. What this does is it breaks this apart into 2 sets of 4, right? I've got 4 data values down here now. So what would I do to find Q1 then? Yes, I would need to average these 2 values right here to find Q1. So my Q1 would actually be the average of these 2, just like I would average the 2 values to find median if I needed to. What would be the average value of 17 and 12? 14.5. And how about the average value on the upper end of this for Q3? It actually ends up being 22 because these two again match. So Q3 is 22. Okay, that worked out nice. Okay, so you do need to be careful that when you're doing the median that you don't exclude things you didn't mean to exclude. For example, let me erase these pieces that we did in orange. What I often see students do when they find a median like we did here is they exclude these 2 values. You don't get to exclude them. They get divvied up and broken apart and sit into their own little corners, right? So you can't just ignore them because that would give you a different answer, wouldn't it? If I exclude those, what's Q1? 12. Okay? So be careful not to exclude something that's intentionally there and needs to be split up. Okay. Let's go back to our data the way we had it, though. Okay. We have the Q1, we've got the median, we've got Q3, and also the median is also called Q2, just to remind you. It actually has a name now. And then the 12 and the 30 are also important values. What are they called? They find the range, but they're called the lower and the upper extreme. So this number right here is my lower extreme. And this one is my upper extreme. Those are the 5 values that I need in order to create a box plot. And so that is actually the directions that we are given on this problem. So how do you create a box plot? We are going to have a box. We're not going to start with a box, though. First, we're going to start with a number line. My number line needs to include the values that my numbers are included at. And they need to be in a proper scale. For instance, it would not be appropriate for me to make a mark for 12, 17, 18, 22, 30, and space them equally apart. Because they're not spaced equally apart, right? There's going to be more distance between 12 and 17 than there is between 17 and 18. So the easiest way to fix that problem is to simply make your chart where you've listed the values out. I'm going to list mine in 3s because it's enough. So I'm going to do 12 to 15, 16, 17. Here's 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. They aren't perfect, and now I've run out of space. Thank goodness for abilities to move things. 28, 29, 30. It all worked out okay. The 5 values that we just got above, lower extreme, upper extreme, the quartile values, we're going to put a dot at each one of those values above my number line. So 12 is one of them. 18 is one of them. Oh, I skipped my 17. 17 was one. 22 is one of them. And 30. All right. It's not the best dot ever, was it? Let me try a little bit better. Okay. What we're going to do is between the first dot and the second dot, we're just going to draw a horizontal line or line segment. And the same thing between the 4th dot and the 5th dot. So we're connecting our lower and upper extreme to the Q1 and the Q3 values, right? In between, there's going to be a box. Yes. So I'm going to draw a box in. Looks something like that.
Oh, that's definitely not fair.
Wasn't that a nice box? Yeah, I don't do freehand very well, but I can do boxes with an iPad. And then we're going to draw a vertical bar right here between, or at our other dot. See, look at that. That was not a good vertical bar. But you know what? We're about to get one. Just like that. This is a box plot. What kind of information does it give you just looking at it? Well, it tells you, especially if you had a whole bunch of values. I know we only have 7 values here, right? But just pretend for a moment that these were the values that represented a bigger data set. Well, it tells you that 25% of your data lie right here, right? 25% are bunched up around this. 25% more are here. And 25% more are here. That's a lot of information. And you had it just like that by looking at it. You can see it, right? That's good. You also can tell me just by looking at this, what's the median? It's 18. It's there, right? What's the first quartile value? 17. Let's say, for instance, that this information represented the length that a child could jump in inches. I think we could do that with these particular numbers. Some child can only jump a foot, 12 inches. Some child can jump almost 30 inches. Okay, let's just use that. Okay, well then what would Q1 mean? Well, Q1 is 17. What would 17 mean?
25% of children can jump 17 inches.
Or less, right? Excellent. That was very well done. That's context, right? It tells me that 25% of the kids have this kind of a reported value. Their value that they can jump is less than 17 or 17 or less. Okay? You could also say that 75% of the kids can jump further than 17 inches, right? That would be the exact same statement, but in the positive sense versus the negative sense, or above that value versus below it. Right? Okay, there's something missing from this, though. A title. Yes, I heard several of you say title. Wonderful. Whoops. What kind of a title could we give this? We don't have any context, so. Was that you, Alyssa? Yes, it is numbers. This would be something. Let's give it some context. Let's use the one we just gave. Can I do that? So this is the inches. Jumped by 3rd graders. I think once we hit 3rd graders, we've got enough difference in the actual lengths of their legs that might actually make sense. Probably not with the 1st graders, right?
Is this linear?
Yeah, like I'm thinking like they're going like that.
I know.
Yeah. No, we're not doing vertical jumps. That would be impressive. Yeah, it would. Or I was thinking like a long jump kind of thing, you know. All right, yeah. Okay, so let's use that so that we could create a title that makes sense. What would the title be for this? So this would be the
Jump distance of 3rd grade.
jumping distance. That would work. What's that?
It looks like it would be like in track, you know? It looks like the box looks like it would be a That's kind of
It kind of does, doesn't it? Jumping distances of 3rd graders. I have to have the units on there somewhere, right?
In inches.
Yeah. In inches. something like that. Got to have a title. All right, any questions on this one? These are actually quite helpful. They're really easy to mark. I mean, like you can draw these pretty quickly, especially if the data sets are small. This data set was quite small. But they give you a lot of information at a very quick glance, which is why they're so helpful.
Does the box become the normal, for example, say, if a kid jumped 16 or 17 or below, he's below range, I guess, or above range?
It could at least be thought of as being the middle 50% of the values, right? So like I know that when my children brought home their student report cards back for like standardized tests, they actually shaded in where the 50% of the values lie. So I could see my children's results compared to everything else, and they considered it to be normal if they were in the middle 50%. They considered it to be above average if they were above that, and then below if they were underneath that 25% value. So in that respect, I think that would be a reasonable way to think about it. But it really depends on the data instrument that you're using and what you're trying to calculate. So, yeah. All right, let's shift gears. Deviation. Deviation talks about how something is spread apart. In other words, variation. We're going to talk about two types of deviation. Well, three sort of. So we'll say three. The first type of deviation is called mean absolute deviation. I'm going to abbreviate it how? MAD. Yeah, I am going to abbreviate it MAD. This makes use of absolute values to find the difference that each data point is away from the mean. It's found by taking absolute value differences and averaging them together. Now, when I do this kind of data, I tend to create a chart. It's the easiest way to handle this and to not lose any of my information or just get confused on it. So you're going to see me doing charts, like a number chart for both this one and the next one. So this is mean absolute deviation. It has to do with absolute values and averaging them. The other one that we're going to do, the other two are related, variation and standard deviation. So variation is a process by which we are trying to find the average of something, but it's the sums of squares. So this is sort of a list of steps that you go through to find variation. The first thing you do is you have to find the mean, if you haven't already. The second thing is to subtract the mean from each number. And we're going to do this with absolute values because we can. And we can because the next step is to square things. And what happens when you square things? To signs. What happens to the signs when you square things? They all turn into positives, right? So from step 2, if I kept my negatives, they turn into positive. If I ignore the negatives because I found absolute values, they're still positives. So there's really no need to keep the negatives in step 2. So we're going to avoid doing that just because we can. After we square the differences that we got in step 3, in step 4 we're going to sum those. We're going to add them together. And step 5 is to divide by the number of values. So that's an averaging process, right? Add something, divide by the number of values. If we're actually finding variance, then we're done. And variance has an abbreviation. Your book is going to use S squared. I know, you wanted it to be V, didn't you? Sorry. S squared. This is a sample variance. There's another notation that you use in statistics, but your book is using this one. Standard deviation simply takes the variance and it square roots it. So what do you think we're going to call that when we take a square root of S squared? S. And now you're happier because S for standard deviation at least feels a little bit better, doesn't it? It does. Standard deviation is S. So the only difference between variation and variance and standard deviation, I got the Asians in there too far. The variance in the standard deviation is the square root. One of them squared of the other one. Okay, so it's just one further step to find standard deviation. All right, so we're going to do an example of these. Have you seen that data set before? No, never. Yeah, we saw it once before, and so like I said, we're just going to keep using it because we can. And it's kind of nice because the first step in any of this stuff is finding the mean. And we already know the mean for this. We found it back on problem number 1. What was our mean value? It was 19.9. So we're going to need that. Well, we already rounded it to 19.9. So we're going to...
Should we have 19.85?
Oh, I see what your question is. We're going to use the rounded one that we have. Yeah, so we're going to leave it with the rounded version. And the only reason that we're going to do that is because it's not going to change the answer too very much. That's why we're keeping the 1 decimal already, is to keep the rounding accurate to a whole number kind of values. So, but yes, the longer you keep the decimal out, the more accurate it's going to be. But it's also going to be more cumbersome to work with if you have more decimal values, right? When you keep more decimals, you have more to keep track of. So, all right, so let's actually create a table for this. So what we're going to do is this one's only going to have 2 columns. The first column is going to be the x values, and if you really want to put them in order from smallest to largest or something like that, that's totally fine. You don't have to. I'm going to leave mine just like they are. The next one is actually going to be the x value you have minus the mean and absolute values. Okay. I'll write out a couple of them, and then you're going to get the hang of it, and you're not going to write it out anymore. So here's the first thing. I'm going to fill in all my data values. It's 18, 22, 22, 17, 30, 18, and 12. So the first thing is to take the 18 minus 19.9, because that's my mean. I'm going to subtract 19.9 from every single one of them, and find the absolute value. So if I take 18 minus 19.9, what do I get? I get negative 1.1, right? Do I want to keep the negative? No, this is absolute values we're working with. So the value I'm writing down here is just going to be the 1.1. Did you guys tell me 1.1? 1.9, okay. I think that's 1.9 is what we want, right? Okay. How about 22? We're going to get a 0.1 on that one. There we go. Yeah, so 22 minus the 19.9 is going to give me, this one's actually positive 2.1. But again, when I absolute value, it all becomes positive, so this is 2.1. And I have another 22 after that, so there's another 2.1. Good job. Okay, how about the 17? 2.9. How about 30? 10.1. 18. 1.9, we already did that one, right? And then 12. 7.9. Okay, so we do the column that's got the absolute value differences between the mean and our value. What we do with mean absolute deviation next is we add this column together. So your calculator can do that pretty quickly for you. 1.9, 2.1, all the way down to the 7.9. We're going to add them all together. What value do you get? Okay, 28.9 sounds good. And then what do you think I'm going to do with the 28.9? This one isn't the squaring process. We'll do squares in a minute. Not going to do square roots either. This is an average one, so what's left in terms of my averaging? Divide it by 7. Okay, so let me go back to the description to remind you what it's actually said. Mean absolute deviation makes use of absolute values. We did that to find the difference the data point is away from the mean. We did that. And then it's found by taking the absolute value differences, those are the differences, right, and averaging them together. Averaging means summing them and dividing by the number of values.
What about step 3 then? It says square the differences from some.
You're looking at variance.
Yes, I am.
Yes, which we will do in a second. We're doing mean absolute deviation first.
Yep.
Okay, so we have to take the 28.9, divide by 7. What are we going to get? 4.1, and I should use approximation because this was not exactly 4.1, was it? Yeah, we actually rounded it to 1 decimal point. 4.1. Okay, is that good for everyone? 4.1? Okay, so the other one is the one that's a little bit more involved of a table. We're going to actually find variance next.
So
Yes, Emily?
The absolute deviation is always positive.
Yes. When we are doing this chart right here, we're getting all positives. And we're about to get all positives in the next one, too. Yeah. Okay, variation. I even typoed it here wrong. Apparently, I keep wanting to move my words together. It should say variance. We're going to find the variance for these numbers. And again, you already know the mean. It's 19.9. And that's step 1. So if you want to label your steps on this one, because we do have steps, you could do that to kind of keep track of where you are. So the first thing we do is, just like we did on the last one, we're going to create a table. The table is going to have a column for the x values, but it's going to have 2 more columns after that, not just 1. So we have our x values. That's just our data values. You're going to have x minus x bar. Now, I mentioned this before. Technically, we could leave it like that. But because we're about to square things in a minute anyway, and it doesn't really matter if I have positives or negatives, we might as well just report the positive numbers so that we don't have to actually worry about it. So we're going to square them anyway. Okay? And then the last column is actually taking each one of those values and squaring it. So if you want to think in terms of the steps, this is step 2, the differences. This is step 3, the squares. And then we have more steps after that, but this is the table that we create. Okay, so our table has the same list of values as before: 18, 22, 22, 17, 30, 18, and 12. And it has the same differences from the other chart. We already did that too, right? So I think we had 1.9, 2.1, 2.1. What was next? 2.9? 2.9, 10.1, 1.9, and 7.9. And again, some of those are positive, some of those are negative if I'm worrying about the sign. But here in a minute, it doesn't matter because I'm squaring everything. So now I need to go through this list. You're going to have to help me with your calculator. And we're going to square each one of those values. Okay? And we're going to record them with all the decimals, which will be 2 decimals of accuracy. And we'll round again at the 1 decimal point at the end. Okay? So let's keep our decimals in the middle of the problem for accuracy. What is 1.9 squared? 3 point what? 61? Okay. Yeah, 3.61. How about 2.1 squared? 4.41, and we've got 2 of those. How about 2.9 squared? 8 point what? 41, all right. 10.1 squared. All right. 1.9 squared, we already did that. 3.61. And then 7.9 squared. All right, so look back on your list of steps. Square the differences. We did step 3. What does step 4 say? Find the sum. So we need the sum of all this. What do you get? Thank you, Selena. 188.87. That was step 4. Just for fun, we'll label it. Okay, what's step 5 say to do? Divide it by the number of values. So step 4 and 5 is that same averaging thing that we keep doing, right? Broken into two steps. So we're going to take on step 5, and we're going to take that 188.87, and we're going to divide by what? 7, because there are 7 values. And here's where we will record this to 1 decimal. So just for the sake of having all talked through it, what value do you get with, say, 3 decimals? 981? Okay, so if I want it to record it to 1 decimal, what am I going to get? I'm going to get 27, and I want to say 0.0. That tells it that there's actually a 0 next. Okay, I didn't just round it to a whole number 27. It is 27.0. Okay, and this is my variance, which has the name S squared if we were labeling that, correct? All right, how about part C? I've got the wrong part C on here. Hang on a second. All right, this says B. It's really C. Standard deviation for 18, 22, all the way up to 12. Well, yeah. How do we get standard deviation? Do I have to go through everything again? No. We want the square root of the variance. So S is going to equal the square root of 27.0. Now, it's really not 27.0, right? Your calculator should still have an expression that's got lots of decimal points. So mine, actually, I think I wrote down 4 just on my paper. Yeah, 9814. Most of the time, if I were to square root the 27 and square root this, they're going to be the same, but sometimes not. Oh, thank you. You're right. Whoops. 26.9814, thank you. All right, so when we square root the 26.9814 ... whatever, what do you get? 5.2? Fantastic. Okay, we're going to talk about what the standard deviation does, what it's actually finding for us as we move into this section a little bit further, okay? We're not going to get there today, but when we get to that section, it's going to come up again. So we just have a couple more minutes, so it doesn't make sense for me to do this next piece right here. Well, actually, this is the one I wanted. I just didn't realize it was the exact next thing. Normal distributions. Let me talk about normal distributions. Go ahead and write down this slide. A normal distribution is a smooth bell-shaped curve that depicts frequency values distributed symmetrically around the mean. Okay. The picture that goes along with this looks something like this. Mine does not look very symmetric. Pretend. This value right here at the peak is the mean. Let me move my value stuff up just a little bit. Okay, it's the mean right there in the middle. Should look like a symmetry, a hill. It's symmetric about both sides. Standard deviation is what this is doing next. Empirical rule says 68% of the data is within one standard deviation of the mean. So if I go out one standard deviation, on the last problem, that would be if I went out 5.2 in each direction and the curve were normally distributed, the data were normally distributed, I would have 68% of my data between one standard deviation smaller than 19.9 and one standard deviation bigger than 19.9. If I go out 2 standard deviations in each direction, which would be like going out 5.2 and then another 5.2, right, in either direction, 95% of my data is in between those values if the data is normally distributed. And then if I went out 3 standard deviations, I get 99.8, which is practically everything, right? I mean, almost everything is within 3 standard deviations of the mean. And we're going to work some problems that are going to talk about this and use this empirical rule to do this.